Hello everyone. Let's study and let's see some practice questions from the chapter Chemical Thermodynamics. So let's start. First disclaimer slide which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So this is our index slide and we will going to see today some practice questions from question number 1st to question number 7. So let's start from question number 1st, which says an ideal gas is allowed to expand both reversibly and irreversibly in an isolated system. If Ti or T initial is the initial temperature and Tf is the final temperature, which of the following statement is correct? So you have to find out that which of the statement given in the options is correct. If you have given that Ti is the initial and Tf is the final temperature of an isolated system, right? And in this question, this is mentioned that this ideal gas is performing. So your options are T final of irreversible process is greater than T final of reversible process. T final is greater than T initial for reversible process, but T final is equal to T initial for irreversible process. T final for reversible is greater than T final for irreversible, or T final equal to T initial for both reversible and irreversible processes. So for solving this question, so you have 10 seconds to solve this question, and after that we will see that which statement will be the correct one. Okay, so the correct option is A option. A option means that T final of irreversible process is greater than T final of reversible process. So let's see the solution. So the PV diagram, if we draw for the reversible and irreversible expansion of an ideal gas, it is given like this. So we have a graph here having x-axis and y-axis. On the x-axis we have the volume of reversible and irreversible processes of initial or final state, and on the y-axis we have pressure for reversible and irreversible processes and at initial and final state. So from the ideal gas equation we know that PV equals to nRT, so we can write P equals to nRT divided by V. So for final condition of the temperature, pressure and volume, P, that is pressure for final, will be equal to nRT, that is temperature at final, and upon V at final. So from the curve it is seen that the pressure at final state of irreversible process is greater than pressure of final state at reversible process. So we can see in the diagram that the PF of irreversible process, that is this one is greater than P final of reversible. P final of reversible is this one. So if we see the value corresponding to these terms, so P at final state for irreversible process is here, and P at final for reversible process is here. So of course for the irreversible process P final is greater and then the P final of reversible. So this is stating here, and you can say that T, that is temperature at final for the irreversible process, is greater than T of final for reversible process, which we can conclude from this ideal gas equation, because we can see that pressure is directly related to the temperature of a temperature of a process. So if P is greater, so T will also be greater. That is, P is increasing, T will also increase. They are directly connected. So if P at final state of irreversible process is greater than P of at final state of reversible process, we can say that temperature at final state of irreversible process will be greater than temperature at final state of reversible process. Hence, option A will be the correct answer. Okay, so let's see the next question. Question number 2. When 1 mole of monoatomic ideal gas at T Kelvin undergoes adiabatic change under a constant external pressure of 1 atmosphere, changes volume from 1 liter to 2 liter. The final temperature in Kelvin would be. So we have given a 1 mole of monatomic ideal gas whose temperature is T Kelvin, and it is going under a process of adiabatic, right, and at external pressure of 1 atmosphere, and the volume is changing from 1 liter to 2 liter, and we have to find out that the change in the temperature will be, right, or what is the final temperature at which our gas will reach 1 mole of ideal gas. Okay, so options are T upon 2 to the power 2 by 3, T plus 2 upon 3 multiplied by 0.0821, T minus 2 upon 3 into 0.0821. So you have to select from these options the correct answer. So you have 10 seconds to solve the question. After that, we will see the answer. Okay, so the correct answer will be D option. That is T minus 2 upon 3 multiplied by 0.0821. So how it will be the correct answer? So we know that for adiabatic change, del E will be equal to del W because Q will become 0, right? And del E, we know we can write it as NCV T2 minus T. And T is the initial temperature which is given in the question. So T2 minus T, and work done we know that will be equal to minus of external pressure multiplied by V2 minus VT. So change in the temperature, change in the volume, right? So this is the final volume V2 and this is the initial volume at T temperature, right? So on equating the both del E and del W values above as per this equation, NCV T2 minus T will be equal to minus P V2 minus VT, right? And we can find out this value, that is pressure is 1 atmosphere we have given in the question. Final volume reaching is 2 and initial volume is 1 liter. So 2 minus 1 will be 1 and 1 into 1 will be 1 and negative sign will be there, so minus 1, right? And here we can write N multiplied by CV. We can write that R upon, okay, so this is gamma. Okay, this is gamma, not Y. This is gamma. Okay, and N multiplied by R upon gamma minus 1 multiplied by the T2 minus T, and it will be equal to this term, and this term we have calculated as minus 1, so it will be minus 1, right? For monatomic gases, we have given that N equals to 1 and gamma will be, this is also gamma, so gamma will be 5 by 3. Okay, for monatomic gases, gamma will be 5 by 3. On putting the value of gamma in this equation and R value, which is 0.0821 liter atmosphere Kelvin inverse mole inverse. So N will be 1, R will be 0.0821 upon gamma will be 5 by 3 minus 1. Multiply by T2 minus T, and this is equal to minus 1. So we can rearrange the terms here and we can find that T2 minus T will be equal to minus 1 multiplied by 5 by 3 minus 1 divided by 0.0821, and T2 can be written as T minus 2 upon 3 multiplied by 0.0821, which is our option D. So the option D will be the correct answer for this question. Okay, so we have used the gamma here in the question, which is for monoatomic gases by 5 by 3. We have used the gas constant. We have used the adiabatic change equation, and where Q will be going to be 0 because it is a adiabatic change, right? Hence, our option D will be the correct answer. Okay, so let's see the next question. Question number 3. Water is brought to boil under a pressure of 1 atmosphere. When an electric current of 0.5 ampere from a 12-volt supply is passed for 300 seconds through a resistance in thermal contact with it, it is found that 0.798 gram of water is vaporized. So calculate the molar internal energy change at boiling point, that is 373.1515 Kelvin. So we have given the current, the voltage, and the time for which the current is applied. And we have given the pressure at which our water is. And we have given the weight of the water which is vaporized. And we have to calculate the molar internal energy change at the boiling point. So options are 37.5 kilojoule per mole, 3.75 kilojoule per mole, 42.6 kilojoule per mole, or 4.26 kilojoule per mole. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so the correct answer will be option A. That is 37.5 kilojoule per mole. So let's see how it will be. So vaporization occurs at constant pressure. Therefore, the enthalpy change is equal to the work done by the heater. Okay. So del H will be equal to work done, and work done we can write it in the terms of current, voltage, and temperature time. That is I cross V cross T. So we have to multiply both the three of them. So it will be coming out as 1800 joule or 1.8 kilojoule, right? So molar enthalpy of vaporization will be del Hm equals to del H upon moles of H2, because we are talking about the water in the question, right? So del H divided by the moles of H2O, which is del H we have find out just we have find out that 1 kilojoule. So 1 kilojoule divided by the moles will be given mass upon the molar mass. Molar mass of water will be 18 and given mass is given in the question, that is 0.798. So on dividing the 1.8 kilojoule to this number of moles of water, the molar enthalpy of vaporization is coming as 40.6 kilojoule per mole, right? And on applying the equation of molar enthalpy of vaporization, del Hm equals to del Em, that is change in internal energy, molar change in internal energy, plus del NgRT, where del Ng is the number of moles of products minus number of moles of reactants, or change in number of moles of products minus number of moles of reactants. So del Hm will be equal to del Em plus RT, because the change is just N is equals to 1 here, right? We have talked about this, and moles are not changing. So del Ng is 1 for the H2O, because it is going to liquid to gas, that is water to vapor state. So no number of mole is changing. So del Ng will be equal to 1. Hence, the molar internal energy of change will be equal to del Hm minus RT. We just rearrange the terms, and on putting the values given in the question, and we have just find out in this term, in this equation, we have the molar internal energy change will be equal to 37.5 kilojoule per mole. So the option A will be the correct answer. Let's move on to the next question, question number 4. 1 mole of CO2 gas at 300 Kelvin is expanded under adiabatic conditions such that its volume becomes 27 times. We have 1 mole of CO2 at 300 Kelvin and adiabatic conditions are given and volume becomes 27 times. So what is the work done in this process? We have given gamma is 1.33 and CV is 6 calorie per mole for the CO2 gas. So options are 900 calorie, 1000 calorie, 1200 calorie or 1400 calorie. So you have 10 seconds to solve this question. After that, we will see the answer. Okay. So the correct answer will be option C. That is 1200 calorie. So let's see how. So for adiabatic condition, we can write T2 divided by T1 will be equal to V1 divided by V2 to the power gamma minus 1. Right? So on putting the values of V1 and V2, we know that V1 is, if V1 is V, V2 will be 27 times of V. Right? So 1 by 27 will be the ratio. And gamma we have given in the question. So 1.33 minus 1, which will be 0.33. So we can write the 0.33 decimal in fraction form as 1 by 3. So 1 upon 27 to the power 1 by 3. And if you find out the 27 cubic root, so it will be coming out as 3. So it will, T2 by T1 will be 1 by 3. So we can write T2 is equals to T1 into 1 by 3, right? And T1 is 300 we have given in the question. So it is T2 will be 100 Kelvin, right? And T1 we have given 300 Kelvin in the question. And thus we can say that T2 is less than T1. As we just find out, T2 is 100 Kelvin and T1 is 300 Kelvin. So T2 is less than Kelvin. Hence, cooling takes place because T2 is the final temperature and T1 is the initial temperature, and temperature is decreasing. So, cooling takes place due to expansion under adiabatic condition. So, del E will be equal to Q plus W, we know, and as this is the adiabatic condition, Q will become 0. So, del E will become equal to W. Q will become 0 for adiabatic change. And sign of W, work done, is negative because the gas is expanding, so work done will become 0. This is a sign convention. So work done will be equal to minus of del E, and del E we can say that CV del T, that is T2 minus T1, and with the negative sign CV will be 6 as given in the question here, and T2 is 100 we just find out, and T1 is 300 we know. So 100 minus 300 will be minus 200, and minus 200 into minus 6 will be plus 1200 calorie. So the correct answer will be 1200 calorie. Hence option B will be the correct option. Let's move to the next question, question number 5. A monoatomic ideal gas undergoes a process in which the ratio of P to V at any instant is constant and equals to 1. So what is the molar heat capacity of the gas? So we have given again a monatomic ideal gas, and it is undergoing a process in which the P to V ratio at any instant is equals to 1. So we have to find out the molar heat capacity of that gas. So options are given as 4R by 2, 3R by 2, 5R by 2 or 0. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so the correct answer will be option A, that is 4R by 2. So let's find out how. The molar heat capacity for any process is given by the following expression, that is this: C equals to CV plus R upon 1 minus gamma, right? And when PV is constant and CP by CV equals to gamma. Okay, so this equation we know is used for molar heat capacity for any process. So here P by V is equals to 1 as given in the question, that ratio of P to V at any instant is constant and equals to 1. So P by V we have given is 1. P by V we can write that P multiplied by V to the power minus 1, and this is constant. So CV will be equal to 3 by 2 multiplied by R for the monatomic gases. So CV value is equals to 3 by 2 R for monatomic gases, and we can write this value of CV in this equation. So C value will become 3 by 2 R plus R upon 1 minus gamma will be minus 1, because we can see here in this equation PV to the power gamma will be constant, right? Ideally. So gamma is minus 1 here. So 1 minus minus of 1. And it is coming out as 3 by 2R plus R by 2. Because minus minus will cancel out and 1 plus 1 will become 2. And this will become 3 plus 1, 4. 4 divided by 2R. So the correct answer will be 4R by 2. Hence, option A will be the correct option. Okay, let's move to the next question, that is question 6th. Calcium carbonate exists in two forms, calcite and aragonite. The conversion of 1 mole of calcite to aragonite is accompanied by internal energy change equal to plus 0.21 kilojoule. Given that densities of calcite and aragonite are 2.71 gram centimeter per cubic and 2.93 gram centimeter per cubic respectively. So the enthalpy change at the pressure of 1 bar we have to find. So options we have given that options are 200.72 joule per mole, 309.72 joule per mole, 209.72 joule per mole, or 315 joule per mole. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so the correct option will be C option. That is 209.72 joule per mole. So the change in enthalpy is given by this equation. That del H, change in enthalpy, equals to change in internal energy plus pressure times change in volume. So here del U is given as 0.21 kilojoule per mole. So it will be 0.21 into 10 to the power 3 joule per mole, or we can write 210 joule per mole, right, on multiplying 10 to the power 3. So pressure is given as 1 bar, that is 10 to the power 5 Pascal, and del V is the molar volume of argonite, right? Or we can say that del V is the molar volume of CaCO3, because argonite is a form of calcium carbonate and calcite is also a form of calcium carbonate. So molar volume of calcium carbonate will be 100 divided by 2.93, that is density of argonite, minus 100 divided by 2.71, that is density of calcite, centimeter cubic per mole. And we know that molar mass of CaCO3 is 100 gram per mole. So it is coming out as 100 multiplied by minus 0.22 divided by 2.93 multiplied by 2.71. We just take the LCM here, and it is coming out as minus 2.77 centimeter cubic per mole. We can write it in the meter, that is minus 2.77 multiplied by 10 to the power minus 6 meter cubic, right? We know the equation is this, that del H is del U plus P del V. On putting the values, del H will be, del U is 210, we just find out here, plus P, that is 10 to the power 5 Pascal, multiply by the del V, that is minus 2.77 multiply by 10 to the power minus 6 meter cubic, and it is coming out as 210 minus, because plus minus will become minus, 0.277 joule, and it is equal to 209, that is 209.72 joule per mole, right? Here also per mole will come. Okay, so our oral answer will be 209.72 joule per mole. Hence option C will be the correct answer. Okay, so let's move to the next question. Question number 7. Identify the correct statement regarding a spontaneous process. So we have options here. For a spontaneous process in an isolated system, the change in entropy is positive. Next, endothermic processes are never spontaneous. Exothermic processes are always spontaneous. Lowering of energy in the reaction process is the only criteria for spontaneity. So you have to find out the correct statement among them. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, so the correct option will be A option. That is, del G is less than 0 and del S will be greater than 0. So A option will be for a spontaneous process in an isolated system, change in entropy is positive. So how we can see that for a spontaneous process, we know that del G, that is change in Gibbs free energy, should be negative. And if we see this equation of del G, which is del H minus T del S, if del G should be negative, then this term should be in positive, right? So this should be higher. So that minus term will dominate. So we can say that del H, that del S, that is change in entropy, should be greater than 0. That is positive, right? Because neither T or neither del S could be negative, because if they any of them will become negative, so negative negative will become positive and del C will become positive. But for spontaneous, del G is negative, so del S should be greater than 0, that is positive. And also we know that the total entropy change will be equal to the system entropy change plus the surrounding entropy change, right? And del will come, right? And it should be greater than 0, right? Total entropy change will be greater than 0. And for an isolated system, we know that surrounding entropy change is equals to 0. So the remaining will be system entropy change, which should be greater than 0, that is positive. Hence, option A is the correct option for this question. Okay. Thank you.